Hey everyone. Okay, so what I want to do is take some of the electric circuit stuff we've been doing and start putting some numbers to it and getting the big ideas down. So I've had you do the FET things and look at current and resistance and voltage and some other things. So let's start to put everything down into a model. Okay, so we know the current is the flow of electric charge measured in units of amperes, or sometimes just called amps, and that's symbolized with a capital A. Okay, and just with my note there, I want you to realize that we don't know which direction the charge is going. And the convention is that we always assume that it's positive charge that is moving. That's from the old days of physics, before we understood or even knew that electrons existed and that those were what is actually moving around in our wires. But the basic idea is you get the same answer either way, whether you consider it to be positive charge or negative charge, or it doesn't matter which direction it's going in. Okay, so now here's the question: what do we need to get an electric current? So we know if we have this circuit here with the switch open. By the way, that is what we mean by an open switch. So there is no connection there. We know that current is not going to flow, and we know if we close that switch, there would be a current flowing through here. By the way, just so you know, current is symbolized, so the units are symbolized by capital A, but when the letter that we use to symbolize it is I. So now we would have a current going through the circuit. Okay, so what do we need to get an electric current? Well, we have to have a battery in there. So if we took out that battery, if you just have a bulb and two wires hooked up to each other, you're not going to get any current. The light bulb doesn't light. So we know we need a voltage source, which for us is always going to be a battery. And we have to have basically a path from one end of the voltage source or the battery to the other that is unbroken, a complete route or a circuit. So we need a complete circuit. In other words, a path from one end of the battery to the other. Also in there is that we have to have conducting material. So the path has to be, metal wires. So we have to have conducting materials there that allow current to flow through. Okay, so that's the basic idea. And the next page will come up pretty soon, I think. Okay, so how much current we get depends on two things, and we've kind of saw that from your experience. Excuse me. One is the battery voltage. We know that more voltage equals more current. And the other thing that it depends on is what's in there, the resistance of the circuit. And resistance is, remember, an obstacle to the flow. Or an obstacle to the current. Okay. While I'm at it, I may as well just tell you what the units are for resistance. Resistance is measured in units called ohms. Named after a German guy named Ohm. Ohms are symbolized by a capital omega. Okay, so basically, and we know that more resistance equals less current. And so we put these two things together into Ohm's law. So Ohm's law just basically says the current is going to be proportional to the voltage and inversely proportional to the resistance. In other words, I is equal to V over R. Okay. You will typically see this written out as V equals I times R. Especially in the days before computers. If you were doing it on a typewriter, you could easily type V equals I times R. Doing fractions was not as easy. Okay, so it's a really simple formula to use. So Ohm's law is really important, and we use it a lot. And so we have a voltage source V. We have some sort of resistance there. This is a bulb, but it has a resistance R, and there is some amount of current flowing through. Okay, so very simply, if we have let's say we have a 10-volt battery and we have a 2 ohms of resistance, then we are going to have 5 amps of current going through that circuit. Of course, most circuits have more than one thing. It's not just one resistor or one bulb in there. So we started making changes to the circuit, and we were looking at what happens to the current when you add things. So remember, we have series circuits. Series circuits have one path for the current. So as we add bulbs in series, the resistance of the circuit increases, and the current through the circuit decreases. Okay, and also just for future reference, there may be times where you are asked to compare the brightness of bulbs, or to say how the brightness of a bulb will change if there's a change made in the circuit. And basically, the more current goes through the bulb, the brighter it is. So if you're comparing brightness, you're really comparing current. Okay, so we could think of things in terms of these qualitative questions. The qualitative question, like which circuit has more current through it. So I want you to actually kind of think about that for a second. So looking at these two circuits, circuit 1 and circuit 2, and think about which circuit has more current running through it. Okay. You may even, if you want to pause the video and take some time to think about that, I would encourage that. Okay. So the question is, I think the two common answers would be that 1 is equal to 2, and the other common answer would be that 1 is greater than 2. One of those is correct. So the question is which one? Okay. And hopefully from your experience using the FET, if we think about the reasoning for this, okay, the difference between these two circuits is we have an extra bulb that's in series. Okay. So that is going to increase the resistance in the circuit, and as we saw with Ohm's law, if we increase the resistance, the current is going to go down. So that means that circuit 1 would be greater than circuit 2, and to explain our reasoning, we could say 2 has more resistance due to the second bulb in series. Okay, and so increasing resistance. Decreases current. Now, if we were going to rank the bulbs according to brightness, okay, that means we want to use our greater than, less than, or equal to signs. Again, I would encourage you to take a second to pause the video and think about this for a minute. All right, I will come back with the answer. So the answer is that A is greater than B, which is equal to C. Okay, so as we just reasoned here, 1 is going to have more current through it, okay, than 2. So that means that, let's just say, for example, that because of A's brightness, that represents like 4 amps of current. I'm just making up a number because I didn't give you a battery voltage or a resistance. So we know that this circuit has to have less than 4. Okay, you could probably reason if it's the same, if each of these is the same resistance, we have twice as much resistance, so we'd have half as much current. So this would be 2 amps. And remember, a really important thing is that if 4 amps leaves the battery, all 4 amps have to come back and reach the other, come back. So this, we have 2 amps here, we have to have 2 amps coming back to the battery. So that means that all 2 amps goes through B, all 2 amps goes through C, and so on. So, and again, current is equal to brightness. So A is going to have more current through it, it's going to be brighter. B and C are going to be equal to each other. Okay, so now we look at parallel circuits. Remember, parallel circuits, there's more than one path for current. As more bulbs are added to the parallel circuit, the resistance in the circuit decreases. And the current through the battery increases. Okay, so this is really important. So a lot of students want to just say that adding bulbs to a circuit automatically increases resistance, and that's not true all the time. It depends on whether you're adding in series or parallel. So my analogy to why adding things in parallel lowers resistance is, you want to think of the grocery store. Okay, so if we are here in the midst of this pandemic, and for a while grocery stores were really crowded, people were trying to get all their supplies, and so if you imagine if you're at a grocery store and for some reason there's only one checkout lane open, okay, so that's kind of a bottleneck. So the people going through the store are the current. They're trying to flow out, but they have to get through that. If you open up another checkout lane, then you've made it easier for the current to flow. You can get more people through there per second or per minute or whatever. Okay, and it doesn't even matter if the next checkout lane you open is as fast as the other one. Okay, it might be that one lane has an experienced checkout person, and the other lane is like the new trainee who doesn't know the codes for the vegetables, and things like that. So it's still opening up a new lane, even if it's not the fastest one, makes it easier for things to flow. Okay. So now if we look at this, and again, which circuit has more current through it, and we want to explain our reasoning. So if we look at this, the difference is we've added a parallel pathway here. So that looks to me, that is parallel, so we have less resistance, so we're going to have more current. So if we were explaining which circuit has more current through it, we would say 3 is greater than 1. Okay, so in explaining that, we could say adding a bulb in parallel lowers resistance which increases current. So this this brings up something that is a common misconception. A lot of people want to sort of assume that batteries will always produce the same amount of current, and we can see from these two examples, this one and the previous slide, that the amount of current you get from a battery depends on the resistance that's hooked up to it. So the voltage is the same, but the current can be very different. So if we're ranking the bulbs according to the current through the bulb, it turns out that these would all be equal to each other. I can't remember if I had you do something like that to sort of prove that in there. I'm going to kind of assert this for the moment. Okay, if ordinarily I would have you wire these up in class, and you would see that A and then that these two in parallel would have the same brightness as A, which implies that they all have the same current. So the battery in circuit 3 is going to have to produce twice as much current as the battery in circuit 1. And you could also reason, so like using the example that I used on the previous slide, if that's 4 amps, okay, for that brightness through A, if these are the same brightness, that means this would be 4 amps going through there, and this would be 4 amps going through here. And we know that current doesn't just disappear, so that means that we would have to have, we have to have 8 amps coming out of that battery so that we could split it up into 4 and 4, and we could have 8 amps back. So if you think about it, basically what we said is the resistance in the circuit was just cut in half by putting that bulb in there. So that, I think, brings us, I can't remember what order I put all these slides in, but I think that brings us to the resistors. Yeah, and so resistors. So I've had bulbs in my circuits so far, but we often talk about resistors. So resistors are just circuit elements that are there to have resistance. Like I had, if you've taken, say here, if you've taken anything apart electronic, you've probably seen these like soldered into a circuit board. So their only job is to have resistance, and in very complex circuits what that does is basically regulates the amount of current flowing through the different pathways. So it's measured in ohms, we've said that before, and the symbol in a circuit diagram is a zigzag line like that. Okay, so what we want to do is we want to be able to find the equivalent resistance. So let's say that we have 3 resistors in a row. And let's say that we have 2 ohms and 4 ohms and I don't know, 9 ohms. So the question is, what would be the one resistor that's an equal obstacle to the flow is those 3 put together? Okay. Well, we saw before that adding bulbs in series increases resistance. So the same thing with resistors. So it increases. So it turns out that the answer to this would just be 15 ohms. So in terms of obstacle to the flow of current, one 15 ohm resistor is the same as a 2 and a 4 and a 9 in parallel, or excuse me, in series. And so to generalize, you can probably get this really easily. So if I call these like R1, R2, and R3, then the one that's equivalent, we call that the equivalent resistance, or REQ, that's going to equal R1 plus R2 plus, and I'm just going to put the dot 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 because we could have any number of resistors in series and you just add them up to find the equivalent resistance. Okay. So now if we want to find the equivalent resistance and the current through the battery with this circuit here, okay, this one is pretty straightforward. So if we look at this, these are in series. So Req is just going to equal 5 plus 4 plus 7, which I believe is 16 ohms. And so what I'm saying is that this circuit is equivalent to having our 48 volt battery with one 16 ohm resistor. And so if I want to find the current through that circuit, I'm going to go to Ohm's law, take the voltage divided by the resistance. So if we have 48 volts divided by 16 ohms, I believe that is equal to 3, and that would be units of amperes or amps. 3 amps of current. So that's really easy. I don't see a need to do a whole bunch of those. Okay. Now if we start talking about equivalent resistance in parallel, okay, let me just think of it this way. Okay, so let's start with one resistor. Okay, let's say that's a 12 ohm resistor. Okay, now let's take that 12 ohm resistor and put another 12 ohm resistor in parallel with that. So this is like my grocery store analogy. Okay, so for this, Req is equal to 12. The equivalent resistance now, well, if you think about the obstacle to flow, I've just made it, if you want to think of this, twice as easy to make it flow. So now some of the flow, I've opened up another checkout lane so I can get twice as many people through. So it's half as much resistance. So that equivalent resistance would be 6 ohms. And let's say we add another. So I'm going to open up a third lane. So again, 12 ohms, 12 ohms, and 12 ohms. Okay. So now, if we compare it to the 1, now it's 3 times easier. We can get 3 times as many people through. Okay. And so the equivalent resistance, I would take 12 divided by 3, so Req would equal to 4 ohms. Okay, so in general, if we have we could have basically, so if I have a resistance R and we have N pathways, Req is equal to R divided by N. Okay, but that only works if all the resistors are the same resistance. So you have to be a little bit careful with that. But it's a nice little trick if you do, because it's pretty common to see resistors that are the same. So if we go on, and of course I'm sure you're asking yourselves, what if they're not the same? There is a formula that helps us figure all this out. and at some point the slide will actually change. Okay, so we know that when we add resistors in parallel, that the equivalent resistance has to go down. So the formula that we have is 1 over Req is equal to 1 over R1 plus 1 over R2 plus, and we'll do the dot 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 thing. Okay, so just to show that that works, let's do our example with 3 resistors, 3 12 ohm resistors here. So R1 equals 12, R2 equals 12, and R3 is equal to 12. And so 1 over the equivalent resistance would equal 1 over 12 plus 1 over 12 plus 1 over 12. Okay, so we know we've got fractions, we need a common denominator, we can just add across the top. That's equal to 3 over 12. Okay, but remember that's equal to 1 over Req. So if you want Req, that means you're going to flip it, or reciprocate, to use the fancy language. Is going to be equal to 12 over 3, which would be equal to 4 ohms. Sorry, this equation is important. You should remember that. Okay. So now let's apply that to this circuit below. So now we have 2 resistors that are not the same. Okay. So to find the equivalent, we're going to take 1 over 6 plus 1 over 3, and got to remember our fraction rules. So our common denominator is going to be 6, so we'll have 1 over 6 plus 2 over 6 equals 3 over 6. So the equivalent resistance is equal to 6 over 3, or 2 ohms. Okay, so what we were saying is, in terms of an obstacle to the flow, that circuit there is equivalent to just having a single 2 ohm resistor connected to this 24 volt battery. Now we can use Ohm's law, and I is equal to V over R, so we're going to get 12 amps of current. Okay, so that's simple series and simple parallels. And this is going to be a surprise to me what comes up next. I can't remember. All right. So at this point, with these next couple slides, what I really want you to do is stop the video and go to the FET Circuit Builder app and take some measurements and go ahead and do that, okay? Because we have the idea of battery voltage, but you will also find that you can use a voltmeter to measure the voltage across the resistors. So when we say measure the voltage across a resistor, take the leads of the voltmeter and put them on either side of the resistor, and you'll get a reading on there. And that's still voltage, but it's a little different than battery voltage, so I want you to get a sense of that. So for this slide, and I believe the next one, so we've got some series circuits, and the next page is going to be parallel circuits. So I really want you to go take those measurements and come back, or pause the video or whatever and come back, and then I'll pick it up here in this next slide. Okay. So let's see here. Not sure what I want on that slide. All right, so the loop rule. Let me just say what the loop rule is. So the loop rule says that so if you follow a path from one end of a battery to the other, the sum of the voltage drops must add up to the battery voltage. Okay, so this is a big deal. It's a very, very useful rule. Make your life a lot easier. Okay, so voltage drops would be those voltages you measured across the resistors. So let me go ahead and kind of explain that a little bit, and then we'll go back and see how it works. Okay, so I've got this roller coaster analogy. Okay, so you start here on the roller coaster. So you start, you go up to the top of the first hill, and then you go down, and maybe you do some other things. You might stay flat for a while. So this is kind of a different roller coaster, so we don't go all the way down at the start. Okay, but then you have these drops. But the idea is that by the time you come back around to this side, you have to get all the way down to the bottom. Okay, so our analogy basically goes like this. So the battery is basically like that chain that pulls the cars up. Okay, the cars are basically like the charges that flow through the circuit. So basically that's going to be the current. Okay, and then the elevation is basically kind of like potential energy, or going to represent the changes in electric potential. And electric potential is the voltage.
She's recording her video, so she'll use the 15 minutes.
Okay. So that is basically our analogy. So basically what happens in the battery, one end is low potential, and you can think of this like potential energy, like gravitational potential energy. Low potential, and then we've got high potential up here. And so as the cars move around, they have to eventually drop from high potential to low potential when they get around to the end. That's the idea of the loop rule. And the loop rule is essentially conservation of energy. Okay, wait for the slide to change. Alright, so I like to do it like this. Okay, so as we look at a circuit, so a little bit of the change here. Sorry, I borrowed this from another presentation. We'll just call that voltage. So we've got a 12 volt battery. Okay, we've got a 4 ohm resistor and a 2 ohm resistor. Okay, so at the idea with a 12 volt battery is that one end has a potential that's 12 volts higher than the other end. So it's really convenient. We're going to say that one end, okay, point A is going to be the high potential end, and basically point F is going to be the low potential end down here at 0. So a 12 volt battery, one end is 12 volts higher than the other. Okay. So if we're following the current around, okay, let's just say that the current is going this way. Okay, we're going to go around clockwise. So A to B, is there a drop in potential? I didn't have you do this, but if you used the app to measure this or did it in real life, you'll see that this is just connecting wire, and two ends of a connecting wire, they're always going to be the same potential, so nothing has changed. So remember, the voltmeter measures the difference in potential between where you place the two things, the two leads. So the voltmeter would read 0 if we placed it at A and B, and what that means is A and B are at the same potential. So if A is at a potential of 12, B is at a potential of 12. Okay. Then from B to C, we're going to have a drop. If you put your voltmeter there, you're going to measure a voltage drop, and from D to E, there's going to be another drop. And those two drops have to add up to 12 volts. Okay. Now, we don't have the same resistance. So the question is, if we're talking about energy, are we going to use more energy going through a 4 ohm resistor or a 2 ohm resistor? Well, if you think about it, the 4 ohm resistor is harder to get through, so there's a higher energy cost. So we're going to have a bigger drop in potential there. So we have two drops. They have to add up to 12, and one of them is going to have to be bigger than the other. As a matter of fact, it's going to be twice as big. It's going to be proportional. So I'll show you how to get by with that with more than just reasoning. So two drops that add up to 12, one of them is twice as big as the other. So we're going to have a drop of 8. So going from B to C, we're going to drop by 8. So we're going to have a voltage drop there. Okay, C to D is connecting wire, no drop there. And then from D to E is going to be the other drop, that 4, and so on. So we have the drop in electric potential here, and then another one going through that resistor. Okay, so this is the idea of voltage drop. So you often hear that terminology. So there's two ways to think about voltage. You have the battery voltage, which is like pushing the current through the circuit, and then you have the voltage drop, which is about, how much energy is lost as we go through a resistor. So that is also a voltage drop. Okay, so the equivalent resistance of the circuit, this is series, so the equivalent resistance is 6 ohms. You just add them up. So the current through the circuit, I is equal to V over R. So that's going to be 12 volts. Our resistance of, excuse me, 6 ohms. So we're going to have 2 amps of current. Okay. So the voltage drop, we just kind of reasoned through that the voltage drop for the 4 ohm resistor is going to equal 8 volts, and this one is going to equal 4 volts. But one thing I want you to notice is that when we find the potential difference or the voltage drop, we can use Ohm's law again. Okay, so if we use V is equal to I times R, we see that we have 2 amps of current going through a 4 ohm resistor, so I'm going to have 2 amps times 4 ohms, so that would be equal to 8. And down here we have V is equal to I times R, so we'd have 2 times 2, which would equal 4. So that's a really important thing. So Ohm's law can be used on an individual resistor to relate the voltage drop and the current and the resistance, or we can talk about the whole circuit. The current through the circuit is equal to the battery voltage divided by the equivalent resistance. Okay, so that is also a really useful thing. Now if we look at this in parallel circuits, wait for our last slide to come up here. So in parallel circuits, if we look at this current, there are two pathways for current. Okay, so the current can go this way, and then it can split up either this path or that path. So when it comes to our pathways, remember, current is made of individual charges. One individual charge can either go through the 2 ohm resistor or the 6 ohm resistor, but it can't go through both in the same trip around. Okay, so we actually have two pathways. So let's say we take the outside pathway. So point A is still 12 ohms. A to B, there's no drop there, so that would still be at 12. B to C, we're still going through connecting wires, still no drop yet. Okay, now as the current goes through from C to D, it is going to drop. There's an energy cost to going through that resistor, and that's the only drop. And we know that point F is going to be here at 0. So and from E to F, all connecting wire, that's still at 0. D to E is still at 0. So we've got one drop, and that one drop is going to be all 12 volts. I really missed that badly. All 12 volts are going to be there. So that is this outside path. Okay, and then I'm going to switch colors. Let's go for obnoxious green. So another path is from A to B to E to F, taking that path. So we can go A to B. E is down here at 0 again, and F. So in this case, we have all 12 volts, but we have that different path. Okay, so if you think about it, the voltage drop across any two resistors that are in parallel has to be the same. And in this case, for a simple parallel circuit, the same as the battery voltage. So the voltage drop across the 2 ohm resistor is equal to 12 volts. Okay, and we use the loop rule to figure that out. And across the 6 ohm resistor, it's also 12 volts. Again, the loop rule is our explanation. The equivalent resistance of the circuit, well, let's figure that out. So 1 over Req is equal to 1 over 2 plus 1 over 6. So we're going to have 3 over 6 plus 1 over 6, 4 over 6. So Req is equal to 1.5 ohms. So the current through the battery is going to be V over R. So we've got 12 divided by 1.5, which I believe would equal 8 volts. Now let's think about it. 9 volts, or 9 amps. 9 amps of current. Okay. So when that current gets here, here's something interesting we haven't run into very much of. So the 9 amps are going to get here to point B. They're going to split up. Are they going to split up evenly? No. Okay. So if you think about it, go back to our grocery store analogy, it's a lot easier to get through 2 ohms of resistance than 6. So more customers are going to be able to get through this checkout line than that one. But that doesn't mean nobody's going to go through here. So more current's going to take the easier path. But it's not 50-50, but it's not 100-0 either in this case. So to figure out that current, I can apply Ohm's law to just this 2 ohm resistor. So if I look at that 2 ohm resistor, okay, it's got a voltage across it of 12 and a resistance of 2. So that is going to be 6 amps that way. And then for the 6 ohm resistor, I is going to equal V over R. So it has 12 volts, a voltage drop of 12 volts, and its resistance is 6 ohms. So that's going to be 2 amps, which means, was I wrong? Did I do my math wrong here? 1.5. Yeah. So that would be 8 amps, right? Yes, that would be 8 amps, not 9 amps. Okay, which brings us to another rule, okay, is that when current splits up, the current, so at point B, the current into point B has to equal the current out of point B. That's called Kirchhoff's current rule. We'll get to that in another screencast. Well, this is very long. I'm sorry for how long this took. But thank you for your attention, and that'll be it for us.